Yes. Hello friends, welcome to the session. Continuation of chapter 4. Yes. In the last session I discussed in detail about what exactly 180-degree mode of operation. Then here we concentrate on a three-phase bridge inverter in 120-degree mode of operation. That is three-phase bridge inverter. Three-phase bridge inverter concept continuation. Three-phase bridge inverter. Here I am discussing 120-degree mode of operation. Okay. Just you know this circuit, no need to draw this, that you already know. You already written this one. Once again, here I am drawing. Explaining for R load. Resistive load means no need of feedback diodes. This three-phase bridge inverter circuit. VSC supply. S1, S3, S5, S4, S6, S2. Okay, circuit you already know. This is A phase. This is B phase. And this is C phase. This is R, neutral, A phase, B phase, C phase. Understood? Now this is the three-phase bridge inverter circuit. Now I want to explain this concept in 120-degree mode. Then what you mean by 120-degree mode means? In 120-degree mode, each switch is allowed for a conduction of 120 degrees. How it is allowed for a conduction of 120 degrees means 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1. If you allow like this, then it is called 120-degree mode. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1. This is how many degrees? 60 degrees. This is also 60 degrees. This is also 60 degrees. This also 60. This also 60 degrees. And this also 60 degrees. 60, 120, 180, 240, 300, 360. Yes. Each device is allowed to conduct, each switch is allowed to conduct for an angle of 120 degrees. We will see. Here 2 is triggered. How much angle 2 is conducting? 60 plus 60, 120 degrees. Here 3 is triggered. How much angle 3 is conducting, you tell me? Yes. Here 3 is conducting. Here also 3 is conducting now. 60 plus 60, 120 degrees. Here 4 is triggered. How much angle 4 is conducting? 60 plus 60, 120. Each switch is conducting 120 degrees. That's why it is called 120-degree mode of operation. Then whatever the analysis I done in the case of 180-degree mode of operation, same analysis we want to do here. Yes, sir. That means if the different devices are conducting, we want to calculate what the phase and line voltages. By calculating phase and line voltages, then we can draw the waveforms. After drawing the waveforms, from that waveforms we can list out some points. Those points are important for any competitive point of view. Then after drawing the waveforms, then we can do the analysis. Okay, this concept I want to discuss in 120-degree mode of operation. Yes, tell me. Let us assume that we are not drawing the waveforms. We are drawing the waveforms after conducting the some devices. Then we are not drawing the waveforms at starting. Let us assume that already 1, 2, 2, 3, 3, 4 is already conducting. Let us assume that now 6, 1 is conducting. Okay, if 6, 1 is conducting, what is the phase voltage and what is the line? Once you can calculate the phase voltage, calculation of line voltages are very easy. That you concentrate. First you tell me, 6, 1 is conducting. If 6, 1 is conducting, then you calculate what is the phase voltage and what is the line voltage. 6, 1 is conducting means from this we can draw the circuit, equivalent circuit. Directly I am drawing. 6 means which phase? B phase. 1 is which phase? A phase. 1 minute please. 1 is conducting, 6 also conducting. But A is not. 5 and 2 is not conducting. In A phase 1 is conducting. In B phase 6 is conducting. No device in C phase. No device in C phase. This is A phase. This is B phase. This is C phase. This is neutral point. Okay. Now in A phase 1 is conducting means A is connected to which plate? A is connected to positive plate. That you draw the circuit. Equivalent circuit. This A phase is connected to positive plate. And this point is which one? Neutral. Next. What about B phase? This B phase is connected to which plate? Negative plate. B phase is connected to negative plate. This is R. This also R. This is B phase. Let this is V. Let this current is I. Now can you define what is I equal to? Then I equal to Vs by 2R. Then first you define VAN. VAN equal to I into R. That equal to Vs by 2. Yes. Now you can define current is enter at neutral point now. Wherever the current is entering, from that point you can define the voltage. Then you can define VNB. We get Vs by 2. But you want VBN minus Vs by 2. That means if 6, 1 is conducting, A phase voltage is plus Vs by 2. B phase voltage is minus Vs by 2. But what about C phase voltage? No device is conducting in C phase voltage now. Vcn equal to 0. But every time drawing the equivalent circuit, doing the analysis is a lengthy procedure. Now without doing this analysis also, directly you can write the formulas. We can write phase voltage formulas. Once you can write the phase voltage formulas, calculating the line voltage are very easy. Yes or no? For example, VAB you want, VAN minus, like that, VAN minus VBN, VBC, VBN minus VCN, VCA, VCN minus VN, that like that you can calculate. That I already explained. Okay, now, see without doing analysis, in order to write the A phase, B phase and C phase voltages, see the one observation here. Now, if any phase is connected to positive plate, plus Vs by 2. If it is connected to negative plate, minus Vs by 2. If it is not connected, 0. This observation now. If any phase is connected to positive plate, plus Vs by 2. If it is connected to negative plate, minus Vs by 2. If it is not connected, 0. Now with that observation, here 6, 1 is conducting. This is A phase, this is B phase, this is C phase. Similarly, you tell me. 1, 2 is conducting. 1 means which phase? A phase positive. 1 means A phase positive. A phase positive. Then what is VAN equal to? Vs by 2. 2 means which phase? C phase negative. C phase negative. What is VCN equal to? Minus Vs by 2. Then what is VBN equal to? 0. Like that you can write. Tell me. If 2, 3 is conducting, all these formulas you can list out. If 2, 3 is conducting, you tell me. 2 means which phase? 2 means C phase positive. C phase positive means VCN equal to plus Vs by 2. Sorry, C phase negative na. 2 means C phase negative. This is 2. 2 means C phase negative. C phase negative means this is minus Vs by 2. Then 3 means which phase? B phase positive. Then what is VBN equal to? Plus Vs by 2. Then what is VAN not connected na? 0. VAN equal to 0. Similarly, you can write this is 1 2, this is 2 3. Similarly, you tell me 3 4 is conducting. 3 means which phase? B phase positive. What is VBN? Vs by 2. 4 means which phase? 4 means which phase? 4 is A phase negative. What is VAN? Minus Vs by 2. Then what is VCN? VCN is 0. Then 4 5. 4 5 is conducting. Tell me. 4 means which phase? 4 means which phase? A phase negative. What is VAN? Minus Vs by 2. 5 means which phase? 5 means which phase? 1 3. Then that is C phase positive. What is VCN? Plus Vs by 2. Then what is VBN? 0. Like this. This is 3 4 is conducting. What is the A phase, B phase, C phase? 4 5 is conducting. What is A phase, B phase, C phase? Like this, we can write any voltage. Similarly, you try for 5 6 also. 4 5 5 6 also you can try. Like this, we can get different phase voltages. Once you know the phase voltage, calculation of line voltage are very easy. Then with this knowledge, now you can list out the waveforms. Here for simplicity, I am drawing 3 phase voltage waveforms and 1 line voltage waveform. That you concentrate. So parallelly, all of you draw the waveforms. Yes. Sorry. This over? Completed? Okay. I want some space. That's why. It's over? Now you can. This omega t. Concentrate on 3 phase voltages, 1 line voltage. A phase. It's also omega t. This B phase. This C phase. One line voltage wave. this omega t. Omega t. Okay. This plus Vs by 2 minus Vs by 2. Plus Vs by 2 minus Vs by 2. Plus Vs by 2 minus Vs by 2. Understood. Then represent. This is A phase voltage. This is B phase voltage. Then this you draw as a C phase voltage. And we are drawing one line voltage, VAB. Okay. This is 6-1 is conducting. 1-2 is conducting. 2-3 is conducting. 3-4 is conducting. 4-5 and 5-6. This we are getting. This 6-1, 1-2, 2-3, 3-4, 4-5, 5-6. This total is one cycle. Omega t. This total is one cycle. Omega t. This omega t. Okay. Up to this you take. Okay. Now tell me. Now we are drawing A phase, B phase and C phase voltages. First you draw the A phase voltage waveform. Tell me. If 6-1 is conducting, what is the A phase voltage? Plus Vs by 2. Okay. 6-1 is conducting. A phase voltage equal to plus Vs by 2. If 1-2 is conducting, what is the A phase voltage? That I given already. 1-2, I already list out that you know. 1-2 is conducting. What is the A phase voltage? Plus Vs by 2. 2-3 is conducting. What is the A phase voltage? 0. That you know already. That all the phase voltage I already given the list according to that I am drawing. 3-4 is conducting. Plus Vs by 2. 4-5 is conducting. Plus Vs by 2. 5-6 is conducting. 0. Similarly, tell me, B phase. If 6-1 is conducting, what is the B phase voltage? Minus Vs by 2. B phase voltage is minus Vs by 2. B phase voltage is minus Vs by 2. Next, tell me. If 1-2 is conducting, what is the B phase voltage? 0. Okay. Next, 2-3 is conducting, what is the B phase voltage? Plus Vs by 2. 3-4 is conducting, what is the B phase voltage? Plus Vs by 2. Then 0. Then it is minus Vs. All these values I already list out according to that I am drawing the waveforms. Okay. Now you tell me. If 6-1 is conducting, what is the C phase voltage? 0. C phase voltage equal to 0. 6-1 is conducting. C phase voltage 0. If 1-2 is conducting, what is the C phase voltage? If 1-2 is conducting, what is the C phase voltage? Minus Vs by 2. Then again, this is minus Vs by 2. This is 0. Plus Vs by 2. Plus Vs by 2. Like this we can get the wave shape. This is A phase, B phase and C phase voltage wave shapes. Understood? Okay. Then this I am drawing phase voltage. Then how to get line voltage waveform? Yes. If you want VAB means what you can do? VAN minus VBN. VAN minus VBN. VAN minus VBN. Just we are subtracting the phase voltage. Once you can subtract the phase voltages, then you can get the line voltage. Now tell me, VAN minus VBN. This is Vs by 2. VAN minus VBN. Vs by 2 minus of minus Vs by 2. How much you get? You tell me. This is Vs by 2 minus of minus Vs by 2. Then plus Vs. Next. Vs by 2 minus 0 plus Vs by 2. Just I am subtracting. We are getting line voltage. Next. 0 minus Vs by 2. Then minus Vs by 2 you can get. Next. Minus Vs by 2 minus Vs by 2. That's minus Vs. Again minus Vs by 2. This we can get. This is the wave shape. Then what is the amplitude of this one? Plus Vs. What is the amplitude of this one? Vs by 2. Then what is the amplitude of this one? Minus Vs by 2. Then what is the amplitude of this? Minus Vs. Clear? Understand? Okay. These are the phase voltage and these are the line voltage waveform. Exactly reverse now. You compare with 180-degree mode and 120-degree mode. Okay. In 180-degree mode, phase voltage is stepped waveform. Line voltage is quasi-square waveform. But in 120-degree mode, phase voltage is, what is the shape of this one? As quasi-square waveform. But what is the shape of this one? Stepped waveform. Exactly reversed. That's why I told now, why you are operating in different modes of operation means to get the different wave shapes at the output side. Why you are operating in 180-degree mode and 120-degree mode? Different wave shapes means to get the different wave shapes at the output side. But we are converting DC into three-phase AC. It is a AC waveform. But it is a pure sinusoidal? No. But the fundamental component may be sinusoidal. If you consider only fundamental component, that fundamental component may be sinusoidal. If you consider only fundamental component, that fundamental component may be sinusoidal. Like this. Then if we consider only fundamental component, then the fundamental component may be sinusoidal. This fundamental component may be sinusoidal. If you consider only fundamental component, like this you can get. These are the sinusoidal waveforms. These are three-phase voltage waveforms, but it is not a sinusoidal. It is a non-sinusoidal. Okay, that analysis later on we will see. Okay, and these are three-phase voltage and one line voltage waveform I drawn. This how to we are getting this line voltage? By subtracting these two, subtracting these two, subtracting these two, subtracting these two. This we are getting line voltage. Okay. Clear? Understand? Then note down this. Now based on this, we want to list out some points. Those points are important for any competitive point of view. Okay. 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 Now we'll see what are the points important. This is 120 degree. We are list out the points based on 120 degree mode. Yes. Tell me. How much angle each switch is conducting? Easy to tell because it is 120 degree mode now. That's why each switch is conducting 120 degrees. Every point is important. Each switch conduction angle. All of you concentrate parallelly. Note down. Each switch conduction angle. Each switch conduction angle. How much? 120 degrees, because it is a 120 degree mode of operation. Next. At a time, two switches are conducting. At a time, two switches are conducting. At a time, two switches are conducting. Yes. Third one. Each switch is triggered at angle of 60 degrees. Each switch is triggered. Each switch is triggered. How much angle? 60 degrees. Each switch is triggered at angle of 60 degrees. At angle of 60 degrees. Tell me, what is the shape of the phase voltage? The shape of the phase voltage is quasi-square waveform. Phase voltage. Phase voltage is quasi-square waveform. Phase voltage is quasi-square waveform. Quasi-square waveform. Tell. What is the maximum amplitude of line? What is the maximum amplitude of phase voltage? Vs by 2. Yes. Maximum amplitude of phase voltage. Maximum amplitude of phase voltage. Okay. Phase voltage is how much? Vs by 2. Maximum amplitude of phase voltage is Vs by 2. Next. What is the shape of the line voltage? Stepped waveform. 3-stepped waveform. Line voltage is 3-stepped waveform. I'm talking about shape. 3-stepped waveform. What is the shape? What is the maximum amplitude of line voltage? Vs. Maximum amplitude of line voltage. Vs. Okay. Maximum amplitude of line voltage. Line voltage. How much? Vs. Okay. Then I already discussed in 180 degree mode. That point also applicable here. To get the balanced 3-phase voltages, what do you want to maintain? Phase difference between. Why you are maintaining like this? To get the balanced 3-phase voltage. Phase difference between two sequential SCRs. Two sequential SCRs. Either top or bottom. Either top or bottom is 120 degrees. Is 120 degrees. These are the points you remember with respect to 120 degree mode. Now we want to do what is the analysis of line and phase voltages. What is the analysis of line and phase voltages in 120 degree mode? Okay, that you concentrate. Clear? Understand? Over? Okay. Then you go for analysis of line and phase voltages. Yes, concentrate all of you. Analysis of line and phase voltages. Line and phase voltages. Now tell me, for simplicity, for which waveform easy to calculate RMS value? Is it for line waveform or phase waveform? It's phase waveform because it's a constant amplitude. But here amplitude is changing. Then you calculate phase. Then you know what is the relation between phase and line. According to that, you can write the line also. Here I am explaining for star connected load. With that assumption only I am writing the formula. Star connected. Assume that loads are star connected. Tell me, what is the RMS value of phase voltage? RMS value of phase voltage. RMS value of phase voltage. V phase equal to, what is amplitude? Vs by 2. Amplitude is Vs by 2. Square root of. How much angle phase voltage is exist in one cycle? This total is 360 degrees. One cycle, 60 plus 60, 120. 60 plus 60, 120. How much angle is exist? 240 degrees. That is 240 by 360. Then RMS value of phase voltage is equal to Vs by 2 into square root of 2 by 3. How much you get? Vs by root 6. Vs by root 6 value is, what is 1 by root 6 value? Then what is the V phase equal to 0.408 Vs. This is RMS value of phase voltage. Then what is the RMS value of line voltage? RMS value of line voltage. RMS value of line voltage. It is star connected now. The relation you know. VL equal to root 3 times of V phase. That is root 3 into Vs by root 6. Then VL equal to Vs by root 2. What is 1 by root 2? 0.707. That equal 0.707 into Vs. This RMS value of line voltage. So, okay. Tell me. What is the RMS value of load current? That equal to phase current. RMS value of load current. Okay. RMS value of load current. That equal to phase current. I phase equal to V phase by R per phase. Clear? Tell me. Average value of each switch current. ISW average. That equal to IT average. How to write the formula that I already told. I phase into. But here, in 180 degree mode, each switch is conducting 180 degrees. But in 120 degree mode, each switch is conducting how many degrees? 120 degrees. Then 120 by 360. How much you get? I phase by 3. Similarly, you tell me, what is the RMS value of each switch current or RMS value of each thyristor current? The switch may be thyristor also. Then I phase into square root of 120 by 360. Then I phase by root 3. Then what is the 3-phase load power? What is the 3-phase load power? 3-phase load power equal to how much power is delivered? 3-phase load power equal to then what you get? 3 into I phase square into R. That is R per phase. That equal to 3 into V phase into I phase into cos pi. Okay, this is the analysis of line and phase voltages in 120 degree mode. Every point is important that you concentrate. Still I want to extend this concept. What I done in 180 degree mode, like that also I want to explain here. Okay, same concept. Whatever the phase and line voltages we are getting, it is a sinusoidal or non-sinusoidal? Non-sinusoidal. Any non-sinusoidal waveforms are analyzed by using Fourier series. Now I want to explain Fourier series of phase voltage, Fourier series of line voltage. From that you can write 1 or 2 points. Clear? Understand? This note down. Okay. Fourier analysis of 120 degree mode. Fourier analysis of 120 degree mode. Fourier analysis of 120 degree mode. First we can apply phase voltages. First we can apply phase voltages. Then you go for line voltage. Fourier analysis of phase voltages. Okay. Then phase voltage means first we concentrate on VAN, summation n equal to, what is the waveforms we are getting in phase voltage waveform? Quasi square waveform. N equal to 135 up to infinity. Yes, 135 up to infinity. Yes, but I told how to write by your own. One phase is nothing but a one half bridge. One half bridge is nothing but a, what is the formula? 2 Vs by n pi. Up to this you know. But whatever the phase voltage waveform we are getting in 120 degree mode, it is a quasi square waveform. Because of quasi square waveform, what you can get? Cos of n pi by 6. Then sin n, by using Fourier analysis, we can get sin n omega t plus 30. Then similarly, you write VBN VCN. VBN equal to summation n equal to 135 up to infinity 2 Vs by n pi. 2 Vs by n pi. Cos of n pi by 6 sin n omega t minus 90. Then similarly, that no need to concentrate on the function, you concentrate on the magnitude, amplitude only. How to write the amplitude, that you know. Okay. Then VCN equal to summation n equal to 135 up to infinity 2 Vs by n pi cos of n pi by 6 sin n omega t minus 210. That you can write. Okay, these are the phase voltage VAN, VBN, VCN. Now, this is function, all this no need, that you concentrate only in the magnitude, amplitude. Then I want to write, tell me, what is the maximum value of nth harmonic phase voltage? Maximum value of nth harmonic phase voltage. Nth harmonic phase voltage. Nth harmonic phase voltage. How much you tell me? What is the maximum value of nth harmonic phase voltage? 2 Vs by n pi cos 2 Vs by n pi cos n pi by 6. Is okay? What is the RMS value of nth harmonic phase voltage? RMS value of nth harmonic phase voltage. Nth harmonic phase voltage. Nth harmonic phase voltage. How much you tell me? Yes. Root 2 Vs by n pi cos n pi by 6. What is the RMS value of fundamental voltage? RMS value of fundamental phase voltage. Every point is important. See, we are not by hearting this one. From this only we are writing. RMS value of fundamental phase voltage. Fundamental phase voltage. Phase volt. Fundamental phase voltage. S. RMS value of fundamental phase voltage. How much you get, you tell me? This is root 2 Vs by pi na cos 30, root 3 by 2. Then what you can get? Root 3 by 2, root 6 by 2 pi Vs. Root 6 by 2 pi Vs. Okay, that simplify that. We can n equal to 1 you substitute. Then you can get root 6 by 2 pi Vs. This about Fourier analysis of phase voltage. Clear? Okay. Now, you write what the Fourier analysis of line voltages. Okay. This clear? But one observation here. This is cos of n pi by 6 we are getting because of quasi nature na. You substitute n equal to 3, n equal to 9, n equal to 15 and so on. What is the cos of n pi by 6? Cos of n pi by 6 equal to 0. Therefore, all triple n harmonics are absent. All triple n harmonics are absent. All triple n harmonics are absent. That you know. Okay. Now, we concentrate on line voltages. Okay. Now, what is the Fourier analysis of line voltage? Yes, line voltages. Yes. Then VABN. This is summation 6k plus r minus 1, where k equal to 0, 1. Why taken 6k plus r minus 1? Because in a line voltage, what is the shape we are getting? Stepped waveform up to infinity. Then 3 Vs by n pi sine n omega t plus 30. Then what is VBCN? Summation 6k plus r minus 1 harmonics, where k equal to 0, 1, 2 and so on up to infinity. 3 Vs by n pi sine n omega t minus 30. VCAN summation 6k plus r minus 1, because all triple n harmonics are absent. Then 3 Vs by n pi sine n omega t, take minus sine n omega t minus 150. This you can get. Then therefore, in line voltage also, in 120-degree mode, because of quasi nature, in phase voltages, triple n harmonics are absent. Even in line voltage also, triple n harmonics are absent. Therefore, triple n harmonics are absent. Triple n harmonics are absent. Triple n harmonics are absent. Another point, what is the maximum value of nth harmonic output voltage? Maximum value of nth harmonic. How much? Maximum value of nth harmonic line voltage. Line voltage. How much you tell me? 3 Vs by n pi. This indicate maximum value. Then what is the RMS value of nth harmonic output voltage? Line voltage. VA, B, NR. Then 3 Vs by root 2 n pi. What is the RMS value of fundamental line voltage? 3 Vs by root 2 pi. This you remember. Okay, this about analysis of line and phase voltage. Fourier analysis of line and phase and line voltages in 120-degree mode. Even in 120-degree mode also, phase does not consist of triple n harmonics. Even line also not consist of triple n harmonics. That you concentrate. Okay, quick note. This function not important here. Mainly magnitude is important. This only you can remember separately, 3 Vs by n pi. But remaining this in 180-degree mode phase and line, in 120-degree mode phase, how to write by your own amplitude, how to write by your own, that I told. But this only remember separately, 3 Vs by n pi you can get. Because of stepped waveform, by calculating that Fourier analysis, we are getting 3 Vs by n pi. Okay. Okay, this about Fourier analysis of 120-degree mode. Here I want to list out 1 or 2 points with respect to 120-degree mode that you remember. No? Yes. In 120-degree mode also, phase, line and pole voltages does not consist of triple n half. Phase voltage, comma line voltage, and pole voltages and pole voltage does not consist of triplet harmonics. Does not consist of triplet harmonics. Triplet harmonics. That means it may be 180-degree mode or 120-degree mode. Phase and line does not consist of triplet harmonics. But where there exists a triplet harmonics? Only in pole voltage of 180-degree mode. That point you remember. In 180-degree mode, pole voltages only there exist triplet harmonics. Remaining either 180-degree or 120-degree mode, it may be line or phase, you don't have any triplet harmonics. Inherently, even harmonics are absent. Because of that wave shape, you don't have any triplet harmonics. But only in pole voltage of 180-degree mode. But here 120. The pole voltage of phase and the pole voltage and phase voltage is same in 120-degree mode. That's why you don't have any triplet harmonics. Okay, next. Now tell me. In 120-degree mode, what is the sequence of conduction of devices? 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1. Like this, it is conducting. We know this. If you draw the three-phase bridge inverter means, circuit means, okay, this is S1, this is S3, this is S5, S4, S6, S2, this is supply. Now see, here 1 is turn off, here 4 is on. 1 and 4 is on same leg, na? But 1 is turn off, 1 is outgoing, 4 is incoming. But there exists a 60-degree phase difference. After 60 degrees only, 4 is on. But that is not the case in the case of 180-degree mode. That I explained now. That means there is no phase difference, 2 switches in one leg in 180-degree mode, hence there is a possibility of shoot-through fault. But there exists a 60-degree phase difference. 1 and 4 is same legs. 1 is turn off here, but 4 is not turn on here. After 60 degrees only 4 is on. Even though there exists a commutation failure of 1, but 3 is only on. That's why there is no short circuit fault. That's why in 120-degree mode, in 120-degree mode, there exists 60-degree phase difference. 60-degree phase difference. 2 switches in one leg. 2 switches in one leg. 2 switches in same leg. Hence, there is no possibility of shoot-through fault. There is no possibility of shoot-through fault. There is no possibility of shoot-through fault. Shoot-through fault. Next, tell. At a time, how many switches are conducting? Only 2 switches. That's why switch utilization factor is less. Switch utilization factor is less. Switch utilization factor is less. Tell me. Because of at a time only 2 devices are conducting, but in 180-degree mode, at a time 3 devices are conducting, more power is delivered to the load. That's why at a given supply, as compared to 120-degree mode, in 180-degree mode, more power is delivered. That means this you remember as a note. At a given supply, more power is delivered. More power is delivered. More power is delivered. More power is delivered in 180-degree mode. In 180-degree mode, as compared to 120-degree mode. As compared to 120-degree mode. Because where at a time 2 switches are conducting, but in 180-degree mode, at a time 3 switches are conducting. That's the reason why more power is delivered in 180-degree mode as compared to 120-degree mode. Okay. This about in detail about 3-phase bridge inverters. The concept of three-phase bridge inverters is completed. In the next session, based on this concept, we will see some models of questions also. Okay, understand? Clear? Okay, thank you. Concentrate on these points. Okay, say for example, if the question is asked like this, one point I am giving here that you concentrate. Okay, 1 minute please. The question asked like this. For example, a three-phase bridge inverter. A three-phase bridge inverter. A three-phase bridge inverter operated in 120-degree mode. Operated in 120-degree mode. First one, RMS value of fundamental phase voltage. Fundamental phase voltage. How much? You tell me. Dash. What is the answer for this one? √6/2 pi into Vs. Second question. RMS value of maximum value of fundamental phase voltage. Fundamental phase voltage. How much you tell me? Maximum value means √2 times. It is RMS now. How to get maximum value? √2 times. √2 times means what you can get? Into √2. Into √2 means √12/2 pi into Vs. Or you also write like this. If you multiply with √2 means √6/√2. That is you also write like this. √12 means 2 √2 na √2 cancel. √3/pi into Vs. That is simple. I am multiplying with √2 RMS value. Then we can get maximum value. Yes. If it is asked like this. RMS value of fundamental line voltage. Fundamental line voltage. How much you tell me? Yes. 3 Vs/√2 pi. Yes. RMS value of maximum value of fundamental line voltage. Maximum value of fundamental line. Any question we can expect. Fundamental line voltage. How much you tell me? You multiply with √2 na, then 3 Vs/pi. Okay, these are the points you remember with respect to 120-degree mode and 180-degree mode. With this, the three